Hello, I'm Edward Tarte, a math teacher. This is another in a series of solution videos to some of my math challenges. The particular challenge for this video is my math challenge about two graphs. Here is the way I presented the challenge in the original video. This lesson is a comparison of two graphs. Each has an equation. The first one has as its equation y equals 1 over x. I will be drawing a portion of that graph. This is the x-axis. This is the y-axis. When x is 1 in this equation, y is 1 over 1, which is 1. And so we have the xy pair 1, 1. That means I go over 1 and up 1, and I mark that point. Right there. Next, when x is 2, y is 1 over 2, which is 1/2. And so I go over 2 and up 1/2, and I mark that point. That's there. When x is 3, y is 1/3, and so I go over 3, up 1/3. Not as far as going up 1/2. That's that point. And when x is 4, y is 1/4. So I go over 4, up 1/4. Again, not quite as far as going up 1/3. So I have these 4 points, each going up not as far as the previous. I am now going to connect them. The connection forms a curve. There's the curve. It gets lower and lower as it goes out to the right, but it will never get as low as the x-axis because I will always go up 1 over something, a tiny fraction out here, 1/5, 1/6, 1/7, 1/8, 1/9. Eventually, way out to the right, I will go up only a millionth. That is a tiny microscopic length, but it's still up a little bit. And so, as I say, this graph will never touch the x-axis. We are now going to look at an area. The area bounded by this vertical line at 1, the graph itself as the upper boundary, the x-axis as the lower boundary, but having no boundary out to the right. I will shade that area. That's the area I'm talking about. Now we're going to compare this with a second graph where the equation is a bit different from this one. This one was y equals 1 over x. The second one is y equals 1 over x squared. And that means 1 over x times x. When x is 1, y is 1 over 1 times 1, which is still 1. That gives us the xy pair 1, 1, which was the same as in the other graph. I mark that with a point. That was the same, but from here on it's different. When x is 2, y is 1 over 2 times 2, which is 4, 1/4. So I go over 2, and instead of going up 1/2, I go up not as far, only 1/4. That's that point. When x is 3, I go up only 1/9 instead of 1/3, because 3 times 3 is 9. That's that point. And when x is 4, y is not 1/4, it's only 1/16. That's very close to the x-axis, but still above it. And so we have these points. I'm going to connect them with the curve as I did in the other situation. There's the curve. And now, as I did in the other one, I will shade under that curve, again with this left-hand boundary, upper boundary, lower boundary, but no boundary to the right. There is that shaded area. Now, the purpose of this video, the main purpose, is to compare these two areas. As we've seen, they have quite a bit in common. They have as their left boundary the vertical line at 1. Upper boundary is the curve itself. Lower boundary the x-axis, but no right boundary. They both go indefinitely to the right. But now I'm going to make two statements, one about each curve, that are very different from each other. This curve with graph y equals 1 over x, this area is sufficiently large to cover the surface of the Earth 1 billion times. This other area under the graph y equals 1 over x squared is not large enough to cover these two squares. What a contrast. Your challenge is to prove that I am correct. To meet that challenge successfully, you do not have to know advanced math. You do need to know probably that the area of a rectangle is length times width, and you probably also need to know how to add fractions. Other than that, I don't see you're needing advanced math to meet the challenge. Here's my solution. First, taking the graph of y equals 1 over x, I form some rectangles that comprise part of the area under that graph. That is, these rectangles are below the graph itself. Each rectangle is twice as long as the previous one. I begin with this rectangle that has dimensions 1 by 1/2. That's an area of 1/2. The next one is twice as long but only half as high. Length of 2, height 1/4. That also has an area of 1/2. Next one, again twice as long but only half as high. Length of 4, height 1/8. That also has an area of 1/2. And I continue this indefinitely to the right. So I have this sequence of areas, 1/2 plus 1/2 plus 1/2, and so on indefinitely. The sum of these areas can get as large as I want. It can get into the thousands, millions, billions, trillions. There's no limit to it. And so, if I have enough of these 1/2s, I will have enough area to do what I described in the video, to cover the surface of the Earth 1 billion times and more. And because that area is actually less than the area under the curve whose graph is y equals 1 over x, it follows that the area under that curve is sufficient to cover the Earth that many times. Now I do something like that with the other graph, the graph of the equation y equals 1 over x squared. This time, though, my rectangles will be more than the area under the graph. Each rectangle, as in the other situation, will be twice as long as the previous one. The first rectangle is actually a square, 1 by 1. That's an area of 1. That's this rectangle. The next rectangle has a length of 2, but a height of only 1/4. And that is an area of 1/2. The next rectangle has a length of 4, but a height of only 1/16, and that's an area of only 1/4. Continuing in that way, I get this sequence of areas: 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and so on indefinitely. The first two add up to 1 1/2. Next, the first three add up to 1 3/4. The first four add up to 1 7/8. The first five add up to 1 15/16. We keep adding them as we go along, and the sum is always 1 plus a fraction less than 1. That means the sum is always less than 2, even as we go on indefinitely. And since that is more than the area under the red curve, we conclude that the area under the red curve, even as it continues indefinitely to the right, is less than 2 units, 2 square units, which agrees with what I said in the video, that that area is not big enough to cover these 2 squares. So that is my solution to my 2 graphs challenge. Thank you for watching this video.